Welcome PCS members and friends to our today's IBS PCS seminar. It is a great pleasure to have with us today physically also Dr. Jinhong Park from University of Cologne. Okay, we had some echo, so we continue. And today our scientific host is Hichul, and I ask him to introduce our speaker. Please, Hichul.
Thank you. Hello, welcome to the PCS seminar, and thanks audience for joining our PCS seminar. I'm very pleased to have a seminar with Dr. Jinhong Park. I want to briefly introduce today's speaker. He received a PhD in physics, KAIST, supervised by Hong-Sun Shim, 2014, and he moved to Israel, Weizmann Institute of Science. He joined the Yuval Japan's group until 2019, and now he is postdoctoral researcher in Institute for Theoretical Physics, University of Berlin. And today, actually, his research interest in condensed matter theory, many things, interaction and non-equilibrium transport, Moiré systems, and quantum entanglement. Today, he will give us a talk. Title is Engineering Moiré band structure. Okay, let's welcome speaker.
Yes.
You can start.
Yeah. Thanks for introduction. So today, what I'm going to tell you, I'm Jinhong Park from the University of Cologne. So today, I'm going to talk about the Moiré band structures. So I think I realized that I prepared so much slides, and I hope that they can make it. So sorry. Okay. So if you have any questions, please interrupt me. So, okay, so actually my talk consists of the two parts, and part one and part two. And then first of all, I'd like to start with the understanding the features of the Moiré bands of the generic Moiré systems. And then also, then I will talk about the kind of specific model, so namely the Moiré potential model. So, and then actually it consists of two talks. And so I first start with the acknowledgement of my colleagues and my collaborators. So the first of all, Jan Attic, and he did many calculations in part one, and then the Jinhong Park is the main players of the second talk and the second part, and then he did most of calculations, which I'll show you today. And then also I acknowledged my PIs, Mikhail Scherler, Simon Krebs, and Alex Roche, and I especially thank to Dr. Roche because he made me get involved in this very nice project. So, and I start with the graphene, and as you already know, a graphene is it's just a single layer honeycomb lattice made of carbon. So we have A side and B side in the Moiré itself, and then this in the low energy, the Hamiltonian is effectively described by the massless structural union with the linear dispersion. So, and then that a k and a k prime points. So this Hamiltonian is just is described by these Dirac points. Okay, so but this graphene is very fascinating in many sense. First of all, because of the Dirac nature, so we can see the very fascinating phenomena, namely the high temperature, the quantum Moiré effect, or also the Klein tunneling. So there are many Dirac exotic phenomena, but in some sense it's boring because the correlation effect is quite weak. The correlation effect is too weak to induce the correlated the phase, the correlated insulated phase, and very interesting order phase. So how can you induce enhance this correlation effect? So this one can be done by just stacking the one layer on the top of other layers. This is called the twist value. So you can just think about the stacking of the one layer on the top of the other layers, and then you can twist one layers with respect to the other layers. So this is kind of top view of the twist value graphene, and the blue represents the atoms in the upper layers, and red, this is not visible here, but this is the atoms in the lower layer. So when you twist the angle a little bit, so this is theta equal to 10. So you can also see the very nice Moiré structures, Moiré patterns. So the Moiré periodicity is much larger than the atomic size, so atomic distance. And then as you decrease the angle, so then you can get a larger Moiré periodicity. Okay, so this is, for example, theta equal to 3 degree. And then I would like to point out that the theta equal to 1. So in the Moiré itself, already we have the 10,000 atoms. So this is really so large degree of freedom, and then which means that there are so many bands, right? So there are so many bands in the first order Moiré brilliance. Okay, so then what actually the twist by graphene has been recently realized in the Pavlov's group in MIT, and this is the phase diagram, and this is conductance as a function of the carrier density. Okay, so and then this filling, so there's -4. Okay, so let me try. Okay, so can you see this is there is a number here. This number represents the electron filling per Moiré itself in with respect to the charge neutrality point. Okay, so this -2 means that there are 2 holes in the per Moiré itself. Right? So -3 means there's 3 holes. Okay, so and then this is the so this one happens at the magic angle, so theta equal to 1.1 degree. Okay, so then let me zoom in this region. We can at the exactly filling of the -2, that mode insulator emerges. So this is completely correlated insulator, and then if you're a little bit away from the mode insulator, there are 2 superconducting domes. Okay? And this phase diagram reminds the high TC superconducting cuprates, for example. So as you can see, it's half filling. We have antiferromagnetism, which is related to the mode insulator, and then this one is besides the mode insulator, there is also supporting dome. Right, so this is quite a similar phase diagram as the twist layer graphene. Now, I really want to emphasize that there are very nice tunability of the twist layer graphene. So in order to obtain this phase diagram, so this is superconducting cuprates, so you have to change the doping, right? So which means that you have to change the sample. So this is kind of formidable job. So it's very difficult to get out this the phase diagram. But instead, here, so in the twist graphene, you can easily change the carrier density by changing the gate voltage. So this I will come to that point. So, but this is a lot of the tunability. There are a lot of tunability in the twist band. Okay, so apart from this superconductivity and mode insulator, there are also the many the correlated phase, namely the ferromagnetism, Chern insulator, and orbital magnetism, also nematic phase. There are many correlated phase. Okay, so now why the correlation effect can be amplified. So this is one question. So actually, it was predict. I mean, so actually there is a magic angle. So magic angle flat bands. The magic angle. Actually, this was predicted by the Bristol. Sorry, McDonald. Sorry, actually, I don't know. Sorry about that. Okay, so I just briefly why we have the flat bands. Actually, this is really the fine-tuning effect. So let me consider the two Dirac cones. So one Dirac cone comes from the upper layer. So it's the same K point. So upper layer, and the other Dirac cone comes from the lower layer. So they are separated because of the twist. So here, so there's no tunneling at all. So now we turn on the interlayer tunneling, and then this upper, so let me try. Okay, so this region can be split, right? So and then induced. So this by this 2 delta, 2 P per, okay? And then when you increase the this T per and this bands, lower band in the electron side is going down, and this is going up. And then at some point, so it's really the fine tuning, such that these two bands meet together. Okay, so this is kind of magic angle condition. So the 2 T-per is the same as VGK zeta. So I really emphasize that this magic angle is kind of the magic in the sense of the flat band happens in a result of the fine tuning of the parameters. Right? So because in the lot of tunability of the twist angle, so we can change the angle, so change this K zeta, and then so we can obtain the kind of magic angle flat band by matrix. Okay, so and this is the typical band structures. At the magic angle, we have a very flat band near the charge neutral. Okay, so but there are more materials are already around us. I mean, before the twist barrier graphene. So there are many examples. The one example, I mean, so the easiest way to make the new more materials is just stacking the one layer on the top of other layers. So we have the two different van der Waals materials, and then you can just stack the one layers on the top of the other layers. So van der Waals materials can be the graphene or hexagonal boron nitrogen, something like that. So we can just prepare the two the van der Waals materials. So just stack the one layers on the top of the other layers. So, but it's a kind of this van der Waals material can be the building blocks like Lego, right? And but unlike the Lego, this van der Waals materials is not exactly fitted. So to make some Moiré patterns. So this is the kind of difference, but so you can easily make the new Moiré materials by stacking the one layers on the other layers. Okay, so so this is kind of my last introduction slide, and then I really emphasize that there are really a lot of bands, which means that we can add the subtract 1 electrons per unit cell by small change of the small gating, right? So small change of the gate. This one can be easily done, right? So we have the many bands. So and then there are extra tunability at twist angle and adding atoms and different material using different materials, and also making the pressure. Okay, so there are many ways to tune the system. So definitely then we can engineer the band structure, and then also there are so many bands. I really emphasize that there are too many bands in the Moiré system. So some of the bands can be the flat, right? So to enhance the effect of the correlation, and also some of the bands can be topological or
Can you elaborate why it's easier to add one electron?
So because it's by the small gate, a small change of the gate. No, there are many bands, right? So you can easily add one electrons, right? So because I mean, okay, so
you're saying the Moiré instead, not the spectral instead.
Moiré is yeah, in the Moiré is what do you mean by the physical is
Because if you wanna insist that it's better to tune the electron number, you should really compare with the aligned bilayer.
Aligned bilayer. So can you say so? Can you repeat?
So you should compare with the Moiré system with the untwisted bilayer. Then what you said.
So what I'm trying to say, okay, so yeah, let me just estimate the kind of the level spacing. So we have the total, so we have the graphene this bandwidth, right? This one can be just divided by the number of units, the number of the atoms in the per Moiré units, right? So this is just a durable n square, which is very small number. So we can easily change the gate voltage we can easily change the gate the voltage by gating. So this is my point.
But then that is the same for even if you consider just drone folding of the monolayer graphene, that is also the same.
No. Okay. So definitely you're right. But what I'm saying is that so we have the many kind of the so let me so you're completely right. But what I'm trying to say is that so we want to change the filling, right? But this filling per Moiré itself. So this filling can be changed by the gate. So this is just my point. So because this level spacing, typical level spacing is very small, you can just change the.
But in infinite systems, the level spacing is equal to 0.
No, so So we have the graphene. Okay, so you can start with this. Can I write? You can write. Yeah. So we can just write down. So so total bandwidth. So the original the bare so underlying the lattice bandwidth. Let's say that it's just the D, okay? The total bandwidth. Sorry for my bad writing. Okay, so and then in the per Moiré itself, so we have the n squared atoms. So let's say it's just n atoms, for example. Number of atoms are in itself. So this is related with the band, right? So number of it's the same as the number of the bands as well. So this is n. So and then then we have right. So we have those some bands. This the bandwidth should be D. This level spacing between the two level spacing is just the durance n. Right? And then this is quite small, right? And then you can easily change the filling by a small change of the gate voltage. This is just my point. So this is nothing serious. Okay. Okay. So are you happy with this? No.
What I think is also same situation for the monolayer graphene.
Yeah, sure, monolayer graphene, but then it's that something happens. I mean, something happens. There are many correlated phase. I mean, for example, in the
Yeah, but I understand what you're trying to say.
Yeah. Okay. So
thanks for that.
Okay. So then some of the bands they're both flat and topological. So this is a very nice playground, and the Moiré system can be the very nice playground to see the competition between the interaction and topology. So this is and then today what I'm going to talk about is that so my goal is to understand the kind of the generic features of the generic Moiré bands. So it's a kind of many of them are really focusing on the the magic angle flat bands. But now I'm a little bit trying to be away from this issue. So I'm talking about the many different bands. I mean, there are many bands already, and I consider this kind of generic feature of the Moiré bands. And then part two, and then I specifically consider the one the model to namely the Moiré potential model. Okay, so this is kind of the model study. So, and then I first so now I'm going to discuss what I'm going to discuss is about the universal principles of the generic bands in the Moiré system. So specifically I will consider some the generic high energy bands. So whether that is flat or not, and also I want to discuss the kind of the interplay between the quantum chaos and the localization of this high energy bands. Okay, so let me start with this quantum chaos in the Moiré system. So as you can see this Moiré system, so there are too many atoms, so almost at 10,000, and then you can easily see that and this Moiré potential. Okay, so this so let me think about, okay, so right here, so I'm here, okay. So in this region, so the atoms exactly in the upper layers, exactly on the top of the other layers, right? And then if you little bit away from this region, so the Moiré potential varies in space. And then you can see that this Moiré potential can be acted as the kind of the disorder, the random disorder. Okay, so and then also there are the kind of the all-to-all interactions, these regions. So then this one usually give rise to some kind of the quantum chaos. So let me first, I mean, this is just one slide for the quantum chaos, and just you can think about just the equal space energy levels, just the uniform distributions, and this is completely uniform. But when you think about this random distribution in the middle, okay, so now we have the randomness, and then you can see that immediately see that this energy levels are not correlated to each other. So how do you know that? So we here in some energy window, so there are many the energy levels get closer, right? So energy level get closer, which means that there is no correlation. This is a complete different. This is completely different from this level recursion scenario. Here, so there's you can see that the energy levels avoid the crossing. So there's the level recursion for which the energy levels get closer. So this is the signatures of the quantum chaos. So we have a large level.
I ask the question in this way. So you consider the finite system. Yes, this is the size of the 10,000 30 diameter. Yeah, it's not a big system. So you should have the discrete spectrum. Okay, very. Yeah. And then how can we speak about the band and something like this? So we'll investigate the spectrum or closed system, which is discrete spectrum. Yes, of course it has some internal structures, maybe some density, but in the state somewhere as we show. But is it true that this is finite system? And what about, I suppose that you made all your calculation using a computer, what is the boundary condition?
boundary condition.
Yeah. What is a struct wave function?
So they-
what wave function equal to 0 on the
So you're talking about the boundary condition of the discrete spectrum.
boundary condition for the wave function?
Yeah.
Usually, if you can find a system, you say that on the order of system, wave function equal to 0. You can suggest maybe something else, some periodic, and doesn't. Yeah, but what type of boundary condition?
So here, okay. So actually, we use the two approaches. One is just type binding model in the real space, and the other. But then definitely we have the boundary. Type binding models in the real space.
I see.
And then this one can be no, so yeah. So but at the low energy, the boundary effect is very small.
Yeah.
Yeah. Okay. Okay. So and then let's make the naive estimations about quantum fields. Okay. So let's think about just the graphene bands. So at the any of the Moiré bands. So and then the GM is the Moiré reciprocal lattice vector. And the G is the graphene lattice reciprocal lattice vector. The N is the size of the Moiré in itself. Okay, so this one is just given by this. Okay, now we turn on this some I don't know. So the Moiré potential or interlayer tunneling, and then the bands are start to bands like that. The typical the level spacing is okay. So this is really okay. So this delta is just divided by n squared. Okay. And then we call it that this left region on good spaghetti region because this goes straight. I mean the energy levels just go straight, and so there is a level cross. Here, so this is called the levels Cook spectral region. So we can see that there are a lot of quantum tails and there are a lot of level. Okay. So and then what happens to the generic Moiré system? So Moiré potential is a T prime reaper. It goes like 1/n. So this is usual scenario in the experiment, and this one can be much larger than delta. So which means that there are which means that so within the window of the T prime reaper, there are many the levels, energy levels, and they talk to each other, and then we expect that the large the quantum chaos. Okay, so then we expect that the large strong amount of the quantum chaos, and then now we really go to the real calculation. So this is this band structures can be obtained. Yeah.
What about this interlayer coupling?
Interlayer.
You have taken this perpendicular, that interlayer coupling. What about this?
Yeah. So actually, okay. So let me go back. And then this one is related to this. Okay. So actually, it is related to the dispersion, but this has nothing to do with it's not related with this N, right?
No, I'm saying like because in your model you have taken some parameters like interhopping and inter.
Yes, exactly. So this is okay. So okay. So let me so you're talking about the kind of usually the graphene velocity, right? So the graphene.
No. I'm just talking about in your model because you have shown like you are taking some interlayer tunneling, right?
Yes.
Between two dropping layers.
Yes.
And also interlayer coupling.
No. So after that, so Weaver is the Moiré potential. So there are many ways to make the Moiré system. So one way is the interlayer tunneling. So I agree that it's confusing. Okay, so let me T-per is the kind of interlayer tunneling. And then also there are another way to define the Moiré system, like the just Moiré potential. So I will come to that point, but this Weaver is the just Moiré potential, of the upper layers induced by the lower layer. This one also can have the Moiré periodicity. Right? But in this case, but there are two ways, but this is why I just
because I thought that we have tight binding model, so this corresponds.
Right. Sorry. Okay. Okay, so and then here as first of all, I would like to notice that this nice flat bands in the middle. And then here, so as you can see, so there are some level recursion a little bit, but so this higher, generically higher bands, right? So just cross each other, so there's no level recursion. So the estimation says that we have the level recursion, but in real calculations, there's no level recursion. So what happens really? So this I want to answer these questions. So why there is no quantum chaos? And then actually there is another mechanism, the undefined localization mechanism in momentum space. Okay, so let me think about this continuum model. So this in the momentum space. So now we are considering the momentum space, and then we have the first Moiré Brilliant zone. So this the three points. So the k up, and then also the k lower. Okay, and then now I would like to extend it this Brilliant zone like this. Okay, so to form the lattice. Now we have the lattice like this, and then we can construct the Hamiltonian in the momentum space. This is just the usual approach in the continuum limit. So and then there are two important Hamiltonians. So one is the one-side potential, which arises from the graphene dispersion. Okay, so this on-site potential means just graphene dispersion, which does not change the lattice size, and also there's hopping between the neighboring lattice. So this is induced by the interlayer tunneling. So it's just a competition between the two Hamiltonians, and then you can construct Hamiltonian, and then you can diagonalize it, and you can obtain the band structures. Okay. So, and then now we would like to consider some of the Fermi surface. This is Fermi surface, which is related with this energy epsilon. Okay, so this is the Fermi surface, and then the most dynamics they arise along this one-dimensional ring, right? And then so because of the energy conservation. And then this on-site potential, this is very important thing. And this the on-site potential can be acted as the effective disorder. So why is that like that? So here, so this on-site potential of the disk is given by this distance. It's related to this distance. And also in this region, so we have this distance, and then this region, so we have this distance, and then this is kind of the pattern is kind of irregular, right? So this is why we have the we have the disorder, effective disorder, and the hopping. So the hopping is the interlayer tunneling, or the Moiré potential. The general is hopping along this ring, and also the effective disorder. So then we expect that the 1D localization. So because this is also the 1D system, so this the localization should happen. Okay, so this is the picture. So yeah,
Why do you say this is 1D? What am I saying? What is this circle?
this is Fermi surface, and then dynamics. So the through this lattice, this occurs with the same equal energy line. So along the equal energy line.
That's a real stress X and Y.
No. Sorry, this is the momentum space. Yeah.
What is dot?
Dot is okay. So this is the okay. So we have this Brilliant zone.
That's a drop point.
Yeah, Dirac point, and then but there are so okay. So let me elaborate. Okay. So and then this. So yeah. So we have the sum the k point, and the k point we have this kind of point. Okay. And then because of the and then we have G1. 2, blah, blah, blah. And then this one comes from this diagonal part comes from the dispersion. So it is a graphing dispersion. And then this, and then there should be hopping between the lattice. This is generated by this interior tunneling. Okay, something like that. And is it clear or no?
I have a question. Rather than correcting this on-site, why do you assume that the on-site potential in momentum space is really random and not quasi-periodic? Yes, can you go to the next slide?
Yeah.
Because
This one should be quasi-periodic. Yeah. But okay. But what I'm trying to say is that if the epsilon is the energy is quite large, then then we can have the very. I mean, there in some regions. So okay. Let's say that. So in some regions, right? So if the epsilon is large, then we have the many the decay points, and then they feel like the disorder. This is just my point. And say it's eventually this is just what's cost.
Okay, I'm still confused about one dimension because now you're seeing the Fermi surface, which is one dimension, and consider the effects in one-side disorder.
Yeah.
And I mean, even in like a two-dimensional Anderson model, you consider you have one Fermi surface. That's also one dimensional. What's one dimension? What makes one dimension special?
No, actually, what I'm trying to say is that okay. So what I'm trying to say is that the dynamics. I mean, this is it's a kind of the random walk problem. So, but the dynamics usually happens along this energy line, right? Because of the energy conservation. So if you think about the dynamics, right?
Every point are the same energy. The red or blue, they are the same energy.
No,
without intervally conflict.
Let's construct this kind of Hamiltonian. Okay. So and then this one is what is this? This is just a BK. And this one is BK plus G1, something like that. And then this is BK plus G2. So the every points, the on-site potential can be different. So, but the equal energy line, so this energy line has almost same energy, but a little bit disordered. It's not clear or?
Can I ask one more?
Yeah, sure.
So maybe this is not very relevant. So if I understand correctly, what you're saying is you have this one-dimensional effective block diagonalization, which is relevant. Consider the disorder between them, right?
Between them. So can you repeat?
So you're isolating one-dimensional.
Yes.
And consider the disorder problem within that space.
No. So I didn't. So you're talking about the real disorder. So you're talking about the real disorder,
Momentum disorder. Disorder in the moment.
Yeah, but this is what I didn't. Yeah. So actually, this is not the real disorder. But what I'm doing is just the diagonalize this matrix. So I didn't put any disorder here. But what I'm just trying to say is that, so if you just think about this, I mean, okay, so let me clarify. So at this point and at this point, for example, right, have the very similar energy. Okay, but energy is only depends on this radius. But this one has a little bit larger energy than this one. So what I'm just trying to say is that this one can be acted as the disorder. It's not the real disorder.
What determines R? What is
This is some, yeah, the R is determined by the dispersion energy of the point.
Which is
Yeah. So the graphene velocity. Yes.
Yeah, sorry, I'm just reiterating my previous point. So you're saying the larger the R, then the closer the water became to the ground.
Yeah, only in the certain regions. So, but you know that if you see the whole circle, then there's no disorder anymore. So, but if you're really stuck in this regions, for example, I'll come to that point. But if you really get stuck in these regions, for example, then the electron field some a little bit disordered. Okay, so I'll come to that point. So yeah. Okay. Yeah, sure.
Just to clarify. So distance between neighboring the same color dot is hyper A. The A is the initial size of the one layer.
So you mean okay? So okay. So this is so the A is the graphene lattice. Yeah, lattice. And but this is not okay. So I think that this is okay. So this. So let me clarify. Okay. So actually, so this is kind of water space. So this is what I didn't mention very clearly. But this one, so this is kind of the reciprocal lattice spectrum. This is in the water space. Okay, but this is much smaller than the graphene reciprocal lattice spectrum. So it's a much smaller. So yeah, so okay, so what I want to say. Okay, so let me clarify. So we have a kind of the very graphene reciprocal lattice spectrum. So it's just so usual graphene, but this is what you're saying is right, because this is just a divided by it's related to this distance. I don't know, so I don't remember the exact number, but it's around like that, right? But because of the water potential, the water potential is periodic, so we can have some kind of small water brilliance.
Okay. So it is smaller by a factor of n.
Yeah, factor, yeah, exactly.
And so when you write down that type binding model, you can do linearization only when the size R is much smaller than.
Okay, so okay, this is also a good question. So there are two ways. But one is the continuum limit in the momentum continuum model in the momentum space. Then there's a type binding model in the real space. The type binding real space, the type binding calculation is easy. Just that we have we can consider some kind of the graphene lattice, and then we can really consider the effective potential or the interlayer tunneling, or to define with some periodicity. So then you can diagonalize it. So this is one way. But the here is but this other limit is a continuum limit. Is really in the momentum space.
It's approximate.
Yeah, it's approximate. Yeah, exactly. So approximate. Yeah, so approximate, but this is a very So it's a good approximation. Okay, so and then so actually I already came to his question. So okay, so and then there are three regions. So one is the deep localization region, and deeper is much smaller than the epsilon, and also this typical energy scale of the water system, and then this wave function. This is the wave function in the momentum space. This is really got stuck here. So because of the random disorder, right? So this is called the deep localization region. So here, so we have there's a very weak level inversion. So this is completely localized in the momentum space, and then and then maybe if you have the one, for example, if you have the one wave function here and the one wave function here, they do not talk to each other, and then this is why we have the just level. And then, but this is a kind of the 1D delocalization region. So T perp is much is a little bit smaller than epsilon. So here this dynamics really happens along this 1D ring, right? And and then we have a lot of level inversion because we also have the similar wave function close the following this following this 1D-dimensional ring, and then they really talk to each other, and this is why they have a lot of level inversion. So, and then the velocity is quite small in this case. Yeah. So, and then it's quite the extreme limit. So the T perp is much is larger than epsilon. So now it's a completely delocalized in the 2-dimensional space. It's a momentum space, and then the wave function is completely flat. The energy bands are completely flat. So
can I ask?
Yeah, sure.
The more system you considering that this system has the locational strength.
This is so
from your calculation.
It's a really good question. So this is, I mean, this actually, so you know that here, so the wave function is not the it's not there's no symmetry, right?
Yeah.
So there is a symmetry in some high symmetric point, but in the usual the wave function, so in the block wave function is not it does not have any symmetry. But the symmetry is really activated by the interior tunneling. So there is a very interesting point. I mean, this is a very interesting point. Here we have the level crossing here. Even though that there is a lot of level inversion. So, and then we interpret it as the kind of activate the approximate symmetry induced by this interior tunneling. So as you can see, this the wave function is already very, very symmetric. There is some symmetry. Because of this, if you have, you know, that if you diagonalize Hamiltonian, and so if you make a kind of block diagonal form, right? So and then in the same representation they talk to each other, but in the different representation they do not talk to each other. So this is why this crossing, and here this crossing is related to the kind of the symmetry related just crossing. It's nothing. It's a kind of different region. But anyhow, this as you can see, the band is quite band has a lot of level inversion. Is it clear?
Yeah.
Okay. So and then I want to finish by for part 1. So within the experimental parameters, generic bands are not flat in the normal contact test. This is just my answer. And then it's just because of the Anderson localization. So there are many exceptions, but I will not tell you details because I want to go to the part 2. Okay, so now I really specify the one models. It's one Moiré models, and see really what happens. Okay, so in the twist biography, the Moiré periodicity is defined by interlayer hopping, right? So now I'm a little bit different. I'm doing the little different approach in the different the system. Namely, the Moiré periodicity is defined by the Moiré potential. So there's no interlayer tunneling here, interlayer hopping. So the Moiré is just defined. Moiré periodicity is just defined by the Moiré potential. So what is the Moiré potential means really? Okay, so here, so you can see that so there in the Moiré scale, there are some regions which is called AA regions. What do you mean by this AA regions? So A side in the upper layer is exactly on the top of the A side in the B in the lower layer. Okay, so same time is also the BB region. And then there is also the interesting point. So the BA regions, the B side in the upper layer is exactly on the top of the A side in the lower layer. So then you can see that here, so A side in this region, in the region of the BA, under the A side, there's no atoms. So which means that the A side has a different the potential than the different potential from the B side potential. Okay, this is clear. Right. So and then this Moiré potential can vary along this along the over this Moiré. Along with this Moiré periodicity over the Moiré periodicity. Okay, so and then this the potential of the A side is just can be written can be expanded in the reciprocal lattice vector. Sorry that this G is the Moiré reciprocal lattice vector. Sorry, this is maybe I'm confused. I mean maybe you can maybe someone confused with this G, but G is a Moiré reciprocal lattice vector because of the periodicity. So this form has satisfied the periodicity, Moiré periodicity, and also VBR is also periodic, and this one can be written expanded in terms of this G. Okay, so and then now we can also consider the continuum calculations, continuum model, and then you can diagonalize it. And everything, yeah, so you can do everything. Okay, so but the interesting point is that there is the coexistence is the energy window where the 1D dispersing band coexists with the flatness. So this is quite interesting. And this is the band. Okay, so this is the band, and also this band is quite weird already. And then this is the 2D plot. 3D plot, 3D map of the energy in the Moiré reciprocal space, the Moiré first region. And then this the color means that the energy. So this bright color means a little bit larger energy. Dark color means smaller energy. Okay. So and then this, as you can see, this line. Okay, so this is the equal energy line. The equal energy line forms like the pyramid. Okay, this is kind of pyramid structure. And then this and then group velocity is indicated by this arrow. This arrow, you can see that there's no dispersion along this line. Okay. But only that there's group velocity happens like this, right? So it's indicated by this arrow. This is clearly, you can see that this is really the 1D dispersing band. And this is kind of the band structures, following the high symmetric points. And so this is kind of, this is 1D dispersing bands. And on top of this 1D dispersing band, there's also the extremely flat bands. Example here. Actually, I just want to emphasize that this is not the fine-tuning effect. Yeah. So if you change the potential, then also you can have the very similar structure, but with the different coupling and. But okay, so I just want to emphasize that this is not the effect of fine-tuning. So, and then let me elaborate on what really happens in the wave function. This is the block wave function for the flat band. So, and then this the wave function is completely localized in the A8 point. So this is what you can usually expect to be the flat band, because it's the flat band is localized in the real space. And then this one, these three different wave function pressed onto these three different 1D dispersing bands. Okay, so you can see that this wave function expressed only in the one direction, right? And then it's completely localized in the other direction. It's a kind of the one feature. And also, it happens also that this one and that one. And this wave function is obtained from this momentum. And then this, the velocity really corresponds to the spreading direction. So there are three different the 1D dispersing bands. And the point is that this three different 1D dispersing bands meet together at the at the point where the three different dispersing bands meet, the flat bands emerges. So it's a kind of okay. So let me repeat again. So it's a very important thing. So we have the 1D dispersing band like this, right? And then at the junction where the 3 points meet, then there is a flat band. Okay. So how can you understand this 1D dispersing band? Actually, this is already they observed in the real experiment, but I just want to emphasize that this topological origin of this 1D dispersing band is the Hamiltonian is written like that, right? So this is the graphene dispersion, and then this Moiré potential, and also there is two terms. So identity term and the sigma z term. The identity term means that so the sigma z is a pseudo spin, so A side and B side. And so this is the potential. So then there are two terms, and then this one is related to the basket. And so the last term is related to the basket. And then this is the kind of the 3D contour plot. So mass gap is fine, is a positive in the AB regions and the negative in the BA region. There must be that the 1D channels when the sign mass gap changes sign. Right, so this is exactly happens at this point. So this is why the one-dimensional the one-dimension 1D dispersing band is a topological. Okay, so. And then this 1D dispersing band occurs along this vanishing mass gap lines.
What do you mean by topological?
Because this So so when you have so let's ignore that this R dependence. Okay. So let's say that this M is positive, and you can just ignore this stop because it's not very important. And this is mass gap, and let's think about we are in this regions. So then this is M is now the positive. Then we can just draw we can consider some the block sphere, right? And then when you change the momentum, so then this the block the spin covers the half of the block sphere, right? Because this is positive. Now when you change the chemical momentum, so this only covers the half of the block sphere. Okay, and then M is negative. Let's say it's opposite, right? They only covers the other the block sphere, and when you go from this one to this one, right? So then we have the full the covering block sphere. So which means that there should be the topological number which shows that there should be the one dispersing bands. It's a kind of edge states. So so you're familiar with this. So the Chon insulator.
Yeah, so I'm confused about the fermion doubling here because your cover is now half, right? So
this is okay. So this is a good point. So here, so I only consider the K point. So the
cover mine.
Exactly. So this is a good point. So okay. So it's a good point.
So edge mode is actually not.
Edge mode is topological.
Because if you consider K and
no. So K is completely coupled with the K prime.
Because you are considering validity. Because you are assuming the validity.
Yeah. So but the validity coupling is a very nice approximation in the Moiré system. Well, the reason is that so the Moiré potential is quite smooth, right? Smooth means that there is no momentum transfer. So there is no large momentum transfer. So this momentum transfer from the K point and K prime point is exponential sequence. So this is why we only consider K point. This is a really good point. Yes, yes. Yeah. So as he pointed out very well, and then actually there is in the K prime point there is another the 1D chain with the opposite chirality to the K point. So this is just a time reversal pattern. So actually, this is kind of belly hole effect. Yeah. Some kind of belly hole effect. Yeah, but I will come to that point. So okay. So and then the 1D dispersing bands occur along the mass gap vanishing mass gap lines, and then 1D channels can be stable if the width of the wave function, so the channel wave function, can be much smaller than the Moiré periodicity. So this is let me elaborate further. Yeah, so this width is much smaller than the Moiré periodicity. Then this one can be smaller because we can ignore the coupling between the two different coupling between the two wave function. Okay, so
when you say topological, it's also robust against disorder. The real space impurities, but your Moiré potential may be fine, but the presence of impurity, two value couples, and they're not the robust topological.
Yeah, but this is and in the weak disorder, it should be fine. In the weak disorder case, this one should be fine because so they will not change the
okay.
So there should be this one should be the plus. Sorry, this one should be the mass gap is positive and this negative. There must be the line where the mass gap vanishes. But if you have the little disorder, so this one can be changed a little bit. But there should be
the coupling between this 1D mode from the K value and the other 1D mode from the K prime value. They can couple.
Yeah, but okay. So and then the point is that okay. So so in the I think I still feel that this. Okay, so let me a little bit. Okay, so we have the Moiré potential. Okay, this is quite smooth. So we have a little bit disorder, but we can still this one is smooth in the Moiré space. So which means that the Moiré momentum transfer from the K point and K prime point is quite highly suppressed. That's fine. Yeah, and even though that you have a very strong disorder, even though a very weak disorder. But the point is that if you have a strong disorder, maybe this one will change a lot. But this is not
Probably, I think that probably it's just possible that the magnetic impurity although it is weak, it breaks the time reversal strategy, and then probably there's some small overlap there between the time reversal partners there.
But this is a good. So impurity means that we have kind of the very strong potential.
Mm-hmm.
So in that case, right? So we have the overlap between the K and K prime point because there's the large momentum transfer is possible. Yes, and you're right. Also, in the strong disorder limit. So I guess that there's more.
So it's not topological.
Okay, so in the case okay, so. Okay, and so we can discuss. Yeah. Okay, so and then but the flat band has a different origin. So it's just because of the this identity term. So let me draw the form identity term. So identity term forms this kind of quantum well. So this is the this 3D pictures the energy as a function of the positions, and then is a really the potential well. And then this electron is just localized by this potential. It's very strong potential. But actually, what I would like to, what I'm trying to say is that so the formation of the flat bands has a different origin from the formation of the 1D dispersive band, but the both happens only in the very large potential. Yeah, this is kind of my message. So this is why they coexist in the some energy windows. Okay. So and then we can consider some mapping to the condor triangular lattice model. So we can have the minimum model with the 3 1D dispersive band and the flat band, and also there's other degree of freedom and spin and valley degree of freedom, and this is kind of the effective Hamiltonian with this degree of freedom as he pointed out very well, and the valley there's also so the point is that the 1D dispersing bands at the K point is flowing like that, but at the K prime point is a time universal partner, so they are propagating in opposite direction. Yeah, so this is the kind of effective Hamiltonian. So this Hamiltonian for the 1D dispersing bands, and this is the hybridization between the two dispersing band, and so this is hybridization between the flat band and the dispersing band, and this is offside Coulomb interaction. So I really consider some interaction, the effect of interaction of the flat bands, because they are really localized in the AA points. Okay, so now we are in the subspace, namely the total the electron filling of the spin is just 1. So then we have the condor mapping. This two last expression can be written in terms of written as this condor model. Okay, so then we have the condor model, and this is exactly the condor triangular lattice model. And then in this model, you can see very interesting, very exotic the 3 spin term. So okay, so then let me in order to understand this spin-spin interaction for the flat bands. So this is the Hamiltonian, and then we can do the perturbation in J and W, and integrating out the disforming. So then we can make the effective action only effective Hamiltonian for the flat bands, right? So also you have the spin and valley both here, and then there are two important terms. So one is that the sigma the spin-spin interaction. So this is usually antiferromagnetic type the interaction. And this is only, I mean, the important point is that this usual RKQY interaction can be mediated by the different values in the middle. So, yeah, what I mean is that, so you have to round, I mean, this is in order to have the spin-spin interaction between the I side and J side. So we should round, I mean, we should have some rounding. So this is covered by the decay point. This is so one is the mediated by this 1D dispersing channel at the K point, and the other is mediated by the K prime channel. Otherwise, there's no coupling. So this is why we have only have in the valley structures. We have only tau x and tau x and tau y. There's no tau z term. Okay, so the valley changes so in the scattering. Okay, so and then there are also the 3 spin term. So this is the readily it can be just obtained by same valley, mediated by the same valley configurations in the one dispersion channel. Is it clear? Because it's, you can make the loop like this. So this three-spin term can be mediated. So then this is kind of outlook. So I just want to give some outlook about this three-spin term. So three-spin term is written like that. And then as you can see, sorry. So this,
What was the gamma there?
this is gamma is okay. So there is, this is the, sorry, this is, I didn't mention that. Sorry, this is the spin S is the SU4 spin operator. So belly and the spin. So this is really the SU4 space, and then in the 1D dispersing bands. Okay, and then this gamma is SU4 spin operator in the flat band. So this S is the SU4 spin operator for the 1D dispersion band, and the gamma is the spin operator in the for the flat band. Okay, so and then you also have the higher order terms, but it's just maybe important, but maybe not important. May not be important, but I don't. Okay, so then I just
Sorry, what is the sub index I?
is the positions. Okay, so let me.
Position.
Yeah, so it's a good point. Sorry. So this means that this one only. So ijk means just the denotes the index in the triangle. So this is ijk to make the one.
Yeah. No, thank you.
Do you consider real spin or source spin?
This is the real spin. Real spin and the belly. Okay. So yeah. And then I just want to give some.
If you have real spin and belly, then you are integrating your what?
Real spin and belly.
Integrating your out.
So integrate out in the 1D dispersing bands. Yes. So then we can make the effective Hamiltonian only for the flat bands. Right. So this in
terms of spin and belly.
exactly. Yes. Okay. So and I just give you some outlook for the for the future works, and so and then this is very interesting. So this three-spin term is interesting because this one generates some chirality here like this. So this chirality, so this defined here. So sorry. Yeah, here. So this is chirality. So this one can be generated. So and then yeah. So this one yeah. So make some different order states in the tetrahedral order states. But it strongly depends on the formations of the belly texture. So here, so let's say that it's a kind of belly ferromagnet. So two different texture. So I don't know what really happens in the beam field. This is what I'm testing now. But so actually, so what we are testing now. So this belly ferromagnet and this belly antiferromagnet. Okay. So and it turns out that if you compare the two different belly texture, you can have the very different the spin chirality. So here, so in this, for example, in the belly ferromagnet, so this chirality can be the opposite in the two neighboring triangle lattice. So it's kind of a staggered magnetic field. So we have plus here and then this is minus here. Okay, so this is kind of staggered case. But if you have the belly antiferromagnet case, so then we really have the chirality in all triangle. So to break the spontaneous break this time loss symmetry. So and then in that case, we know that the tetrahedral order is possible. This we know that the tetrahedral order this is already known, and also the kind of intermediate the strength of the three spin term, also the chiral quantum speed is also possible. So,
So what is the state you are averaging down to? Calculating this scalar chirality term. What is the state you are averaging over?
sorry.
What is the ground state? So there is an average, right? So you are calculating from average.
Yes. Yeah. And then okay. So and then what I'm trying to say is that let's assume that we have this kind of formation of the belly. But I'm not sure whether this is really possible, but that this is kind of plausible. But if you plug in, and then this one becomes that it depends on the sign of this power jet, right? So okay. So and then it turns out that the different triangle like have the different sign here. Right. So actually this is the same sign. Sorry, this is I'm wrong. The same sign. So it's a very ferromagnet has the same sign in all regions. And then this one should be that this one should be +1 and this one should be -1 to minimize this ambiguity. Is it clear or not?
Okay, so you are saying that this ferromagnetic ground state is basically the ground state ferromagnetic or
This is valley ground state is a ferromagnet in the valley, and then but in the spin texture, so we have the kind of the staggered magnetic field, and then we don't know what will happen. So this is also yeah. But this important thing is that here, so if you have the valley formation, if you have this kind of valley formation, so then the chirality is the same, and then we expect that in the spin cycle, so this we have the tetrahedral order, and this is only for the spin texture, and then in the kind of intermediate strength of the this spin term, and then maybe there is a chiral quantum speed, okay? But this is we are not testing, so actually we don't know that, but we are almost to wrap it up. But okay, so let me look it up. So this is my concluding slide, and then maybe just thank you for listening my talk. Thank you.
Thank you, Jinhong, for this nice presentation. We have time for some quick questions.
I think someone we can articulate. But so when you talk about this valley condensation, valley ordering, so the Ashbin and Michael Jarlatel mentioned about this valley fermion this perspectivity. So
but here
I know they are different orders, but can you comment the relation?
Actually, I don't know exactly, but this is not fermion, right? So this is just the ferromagnet or antiferromagnet. But maybe we can have the I don't know, so more exotic structures. Yeah, but so actually, what is their model? So this is they are considering
they eventually consider the band with the interaction over time interaction with SU4 model. So
yes, so this is just a twist biography.
Yeah.
So
but it's not actually microscopic model in the sense that they just consider SU4 symmetric flat band model. So I wonder what makes different ordering in your case.
Yeah, but actually we don't know yet what really happens in the ground state, but we're almost finalizing this calculation. So maybe some point. But actually, I don't know the connection between their paper and our work. Yeah.
Maybe I got another question. About this non-interactive model you mentioned, when you talk about the quantum chaos, so the Pilkyung and Hoshino actually proposed this 12-side lattice model in the momentum space.
So you mean the binary construction or the what?
The 30-degree twisted variability.
30-degree. Okay.
So somehow that 12 points become ring.
So this is in the Moiré space, and it's in the momentum space or
In the momentum.
it's momentum space. Okay, but actually I'm not sure whether this one will be done right, because so you're talking about 30-degree, right?
Yeah.
So 30-degree is usually the continuum limit, continuum model does not work. So actually I'm not sure whether, because then you have the kind of incommensurate features, right? You should have the incommensurate feature. And this one cannot be captured by this momentum. Momentum is not conserved, right? So you know that this is really the quasi-periodic system. So actually, I'm not sure I don't know. I really know what they did, but actually, I don't think that this continuum calculation works in the circuit.
Yeah. So you show this one-dimensional circle. But the size of the circle cannot go infinite because of these two G vector of the Moiré, G vector of the graphene. Size is always limited by n.
Yes, exactly.
Then I don't think you can see this truly induced localization feature in this finite circle, right?
So okay. So what you're saying is about the right. So this is if you have the very large R. So then we already covered this on the first Brilliant of the But what I want to say is that so this is really small. I mean this we have the 10,000 Moiré Brilliant zone to cover this region. So and then we didn't go to the count the boundary. Actually in the continuum limit, so we don't have the kind of proper boundary. So and then but what I'm saying is that this energy, so we are still in this regions, very close to this region. But still but still you have the many the Moiré Brilliant zone, mini Moiré Brilliant zone.
Then could you give me a number and what is the typical number?
This is n is this total, this is 10,000. So this total number of electrons per so 10,000 is a quite huge number, and then which means that so we have the 10,000 milliband to cover the whole ground.
But when it comes to radius, we have to take a square root of the number.
The radius, right.
Then the
Maybe,
feature won't be right.
So right. Yeah, you're right. Maybe you.
Then that's not enough.
But not. But it's still 100. 100 is also a huge number. Right. But there is a good question. So there's a validity of of this model. No?
Any other questions? Seems not. So in this case, let us thank Jinhong again. And with this, we conclude our. Thank you all.